How you doing, guys? Welcome to the video. We're looking at Fundamental Applied Maths, section 13C, page 225, 226. We're going to look at questions 2, 4, 6 and 9. So dive straight in. Here's question 2. It says a particle moves so that its displacement x in meters from a point P after t seconds is given by x equals 4 cos 2t. Show that it will perform simple harmonic motion, and what is the greatest distance between the particle and the point P? How long will it take to go from a point where its velocity is 0 to a point 2.5 meters from P? Okay, so just to give you a quick idea of what we're looking at here, we've got a particle, so that its distance from a point P. Okay, so P, because this is a cosine function, that's an extreme point P, and its distance from that point is given by it starts at an extreme point. The point still here is P, but our starting point is out here. Its distance from that point is given by 4 cos 2t. And you know the cos, the biggest value we can take is 1, so the biggest value the function can take is 4. 4 is the amplitude, and that's generally the case. The number in front of the cos or the sine is the amplitude. We'll see when we have mixes later on, there's a slightly different approach, mix of cosine and sines. But first of all, to show that it performs simple harmonic motion, you want to show that the acceleration is some constant times the distance. So let's find the acceleration. Well, x is there, dx dt is the velocity, and that's going to be 4, differentiate cos, you get sine 2t multiplied by, according to the chain rule, the derivative of 2t is 2. So that's 8 sine 2t. And then the second derivative, d2x dt squared, is 8 times minus cos 2t, again multiplied by 2, and that's going to give us minus 16 cos 2t, which is 4 times, negative 4 times. So our acceleration is negative 4 times bigger than our distance. Okay, so there we have it. We can say we have therefore shown we're undergoing simple harmonic motion. Okay, omega squared is obviously 4, so omega is 2. And what they ask, well, first of all, sorry, in part 2 they ask what's the greatest distance between the particle and the point P, and that's this 4 meters that we saw for the amplitude, 4 meters. And for part 3, how long will it take to go from a point where it is 2.5 meters from P. So let's suppose we're out here somewhere, 2.5 meters from P, from where its velocity is 0, which is out here, to a point where it's 2.5 meters from P. Okay, so that's from its starting position to a position where x equals 2.5. So we're just going to take our equation and say 2.5 equals cos 2t, and we need to solve that. Okay, excuse me, that should say 4 cos 2t. So dividing through, I'm running out of space here, I obviously mistimed this or misinterpreted this. 2.5t is equal to cos over 4 is equal to cos 2t. So just finishing it off down here, 2t is cos inverse 2.5 over 4. Okay, that means 2t is inverse cos 2.5 over 4 is 0.89 seconds, 89566. Divide that by 2 to get 1t. T is 0.448. Okay, so just to conclude there, t is 0.448. Okay, sorry for cramping that in there. Question 4 asks us if a particle moves so that the distance x in meters from a fixed point O after t seconds is given by x equals 13 sine omega t plus epsilon. When t is 0, x is 5, and the velocity v is 24. Find the value of epsilon, the value of omega, and the value of t when x equals 0 for the first time. Okay, so this is the first time we've seen that epsilon in a question, and I've always said it's an offset. So just to give you, I suppose, well, I'll tell you what, we'll find its value first and then we'll talk about what it represents. So t equals 0, x equals 5, b equals 24. So I can just say, well, x equals 5 equals 13 sine of omega times 0 is 0 plus epsilon. Okay, so 5 over 13 is sine epsilon, and epsilon then is the sine inverse of 5 over 13. Sine inverse 5 over 13. 5 over 13 equals 0.394. 395. Okay, so there's your value for epsilon. To talk about what it is now, I've actually done a little sketch here already for you. What we're looking at here is an offset. That is, we start with a value that's not 0 in our sine wave. We start at 5. Okay, so our full period will bring us back to that 0.5 again. Movement wise, if that's our mean point, and we've got an amplitude in this problem, 13 is that number there, so that's our amplitude. Okay, we're starting not from our mean point, which would be a sine function, and not from our extreme point, which would be a cosine function, but we're starting from here. Okay, so that's where our movement starts from, and we're going to move outwards, back, and all the way back to that 5 meters. That's one full rotation. Okay, so that's what I mean by an offset when we talk about epsilon. This is our max distance here. Yeah, I have that. So where does that 5 come from? I knew I meant to include something else there. That 5 comes from the fact that, well, at time 0, this function here is x equals 13 sine omega t plus that value we just got, which is 0.395. So at time 0, x is 13 sine 0 plus 0.395. And the sine of that, as you might guess, is 5 over 13. So sine of my answer is 5 over 13. Multiplied by 13 gives me 5. Okay, so that's why I'm starting here at 5 meters and starting here 5 meters out from my original position, or from my mean point, excuse me. So carry on with just the maths of it. To find the value of omega, well, our usual v squared is omega squared times a squared minus x squared. V squared is 24 squared is omega squared times a squared is 13 is our amplitude, minus x squared is 5 at that particular point squared. That's a Pythagorean triple. That's going to be 12 squared. So we get 24 squared is omega squared times 12 squared, and dividing across 24 squared over 12 squared is omega squared, and that's going to be 4. Omega is 2 for this problem. And the last part they've said is find the value of t when x equals 0 for the first time. So what we're saying here is x equals 13 sine omega t plus epsilon. Okay, so you're going to say 0 is 13 sine omega t plus epsilon. Okay, so sine omega t plus epsilon has to be 0. So omega t plus our epsilon, remember, is 0.395, has to be the inverse sine of 0. The 13 just cancels there. Well, the inverse sine of 0 could be 0, but if it is 0, then t is going to be negative. So that's a time in this motion before we were starting our 5 meters away from our starting position. So another place where sine 0 is 0, I've got a unit circle for this next question actually, so I may as well come around. Remember, sine is your y coordinate. Your y coordinate is 0 here at 0 degrees. If you rotate around 180 degrees, or pi, sine is 0 again, and again around here at 2 pi at 0 again. So the first time is what we're interested in. That's going to happen at pi 0 pi, or I'll just say 2 pi as well. So omega t will be 0 minus that, so we don't want negative values, so it's either pi minus 0.395, or the next time is at 2 pi minus 3.95. I'm not that interested in that, but I'll just show you where it comes up in the graph. It's the answer we want is this one. Omega, remember, is 2, so that should probably say 2t equals. Okay, so the time that we're looking for is pi minus 0.395 over 2, which is pi minus 0.395 is that divided by 2. We're getting an answer of 1.37 seconds. The next time it happens is at 2 pi minus 0.395, so we'll say 2 pi minus 0.395 divided by 2. The next time it happens is 2.9 seconds later. Sorry, after 2.9 seconds from the start, 2.94. Okay, but that's the answer we're interested in. To come back to my diagram, you can see here times when the value of time is x is 0 for the first time. There's our first one, that's after 1.37 seconds, and then again after 2.94 seconds. That's when we are crossing our mean point, as it were. Question 6 says a particle moves so that its displacement x from a fixed point O time t is given by this function here. So it's a mixture of cosines and sines. If you come back to question 5, you'll see it was all a bunch of things where it's a mixture of cosines and sines. And you can find the amplitude using that formula there, square root of a squared plus b squared. So here it'll be the square root of 3 squared plus 4 squared, which is 5. The omega, in each case, the number in front of the t is your omega. So it's 2 here, it's 4, here it's 1, here it's pi, here it's 3. And it has to be the same. To get that simple harmonic motion pattern, you need the same argument in both your sine and your cosine functions. So this function has the same argument. You can see omega is going to be 1. First of all, prove that the particle will perform simple harmonic motion. Well, to prove that, we'll do our usual dx dt, the velocity, is going to be differentiate cos, you get sine, so that's 12 sine omega t times omega plus, excuse me, that shouldn't say omega, that was just a 1t, sorry about that. So I'm going to scratch that out and just say, well, your chain rule says multiply by 1, which just means you're left with 12 sine t, and that's 35, differentiate sine, you get minus cos t. Okay, the second derivative, d2x dt squared, which gives us our acceleration, is going to be 12, differentiate sine, you get cos. When I differentiated, I got minus sine, excuse me, and that's going to be plus cos. So this whole thing should have come out as minus 12 sine t plus 35 cos t. Sorry about that. Differentiate again, differentiate sine, you get cos, so that's minus 12 cos t. Differentiate cos, you get minus sine, so minus 35 sine t. So our acceleration is minus 1 times 12 cos t plus 35 sine t, which is minus 1 times x. Okay, so acceleration is proportional to displacement, therefore we have simple harmonic motion. And omega here, well, omega squared is 1, so omega is 1. The next part of the question says, find the periodic time. Okay, that's just going to be t is 2 pi over omega, which is just 2 pi over 1, or 2 pi. And find the amplitude. Well, that's using that rule from question 5, the square root of a squared. A is 12 for us and b is 35. So there's part 2. Part 3, the amplitude is the square root of 12 squared plus 35 squared, and that comes out as 37. And part 4 says that find when x equals 0 for the first time. Okay, so x equals 0. Now I can see I'm not going to have space for this, so I'm going to redo this over here. It's question 6. X equals 12 cos t plus 35 sine t. So when that equals 0 is 12 cos t plus 35 sine t. You can bring the cos over, the sine over, it doesn't matter. Minus 12 cos t equals 35 sine t. Okay, dividing through by 35 and dividing through by cos t, we get minus 12 over 35 equals sine t over cos t, and sine over cos we hopefully know is tan t. So t is the tan inverse of minus 12 over 35. Now, if you go to your calculator and you put in what is the tan inverse of minus 12 over 35, you get a negative answer. So let's say, what is the tan inverse of 12 over 35? We get ourselves 0.33 radians. Okay, that's our reference angle. And from our unit circle, we know CAST, tan is negative here. So if our reference angle is 0.33, our argument here is pi minus 0.33. Okay, so the tan inverse of that could be a negative number, which we're not interested in. It could be pi minus 0.33, or it could, again, as you rotate around, it could be out here. It could be 2 pi minus 0.33. If you kept rotating, it could be 3 pi minus 0.33, 4 pi minus 0.33. There's an infinite set of solutions here, but these are the first two. We're only interested in the first solution. So we are going to say pi minus that answer gives us 2.8 seconds. 2.811 seconds. Okay, so that's the periodic time, which is what we've been asked. Oh, sorry, the first time when our position is going to be 0 when we cross our mean point. Finally, question 9. On a horizontal platform in which bodies are resting, a horizontal platform oscillates vertically with simple harmonic motion of amplitude 0.2. What is the maximum integral number of complete oscillations per minute it can make if the bodies are not to leave the platform? So what you have here is this thing is moving up and down. Okay, it's got gravity acting down on it. Okay, and it's moving up and down to here and back to here with simple harmonic motion. Okay, so the fastest we can move it, its maximum acceleration occurs right up here at the top point and down here at the bottom point. Bottom point doesn't matter because the acceleration is going to be back in towards the center, but at the top point, if it is changing velocity faster than gravity, essentially, it's going to pop up. Okay, and we don't want that. We don't want the platform to fall away from it faster than its acceleration. So the maximum allowable acceleration is 9.8 meters per second squared. So our A equals minus omega squared x formula says, well, our maximum allowable acceleration is 9.8 meters per second squared downwards. Has to be minus omega squared times our displacement at that point is the full amplitude 0.2. Okay, so dividing across by minus 0.2, we're going to get ourselves omega squared is 49, and therefore omega is 7. Okay, the question is about how many oscillations we can do per minute, so we want to know the periodic time. So the periodic time is 2 pi over omega, 2 pi over 7, which if we go to our calculator, 2 pi over 7 is about 0.9 seconds. Okay, so about 0.898 seconds. So how many oscillations can we do per minute? Well, that's 60 divided by that number, 2 pi over 7. So 60 divided by our answer is 66.84. It said how many integral number of complete oscillations, so whole number oscillations. We can't do 67 because that will we'll go too fast to get to 67. So we actually have to round down here, and the answer is 66 oscillations. Okay, nice to get a full exercise out of the way in one video. As usual, plenty of other questions for you to give a go, and I'll see you in the next video. Bye bye.